Hi everyone, we are Chenlei and Qicheng from ECHO of Carnegie Mellon University, advised by Professor Sean Blanton. We are here to conclude our project named MADS, a machine learning assisted diagnosis system. The system we proposed aims to utilize various data generated in the testing and diagnosis flow to explore more useful correlations so that machine learning can be used to capture complex behavior and lead to analysis with high accuracy and fast performance among different stages of diagnosis. Towards the goal of building the system, we have accomplished 4 sub-projects with respect to different stages. Project 1 develops an algorithm which adaptively decides the pattern order of each chip for optimal diagnosis outcome. Project 2 and 3 are about diagnosis outcome preview, including a comprehensive diagnosis outcome previewer and the knowledge transferring techniques for model building with limited training data. Finally, in order to improve diagnosis quality, we also developed an enhancement method called LiDAR, aiming for diagnosis results with accuracy and ideal resolution. The first project, test pattern reordering, is motivated by the conflict between diagnosis quality and test cost. In general, the more test response collected, a more precise diagnosis can be obtained. For example, as shown in this figure, if only the test responses for pattern P1 is at hand, then the entire backcone of O1 will be possible candidates. However, if the response from pattern P2 is also included for diagnosis, the possible candidate area can shrink to the overlap of the 2 backcones, leading to a potentially better resolution. Despite the benefit brought by additional field data, collecting more data is not always feasible. For example, collecting more tester data increases cost due to increased tester time and may need excessive memory to store failing data. The trade-off between diagnosis quality and test cost motivates us to find a method that can collect enough failing data with less test cost. In other words, the goal is to apply patterns that are more likely to fail. This goal motivates us to use the idea of recommendation systems. For example, in a movie site, the system wants to suggest movies that each user is more likely to enjoy. If 2 users like the same set of movies, the 2 users are defined as similar. The system will recommend another movie that one user likes to the other. The same idea can be applied in this pattern reordering scenario. If 2 chips fail for the same set of patterns, the 2 chips are similar. The other patterns that fail one chip may also fail the other chip. Applying such patterns first, we are more likely to collect more failing data with fewer patterns. To demonstrate the efficiency of the developed method, the test patterns needed of the new order is compared with the default test pattern order. Assume chips in the test set are tested with 2 orders: the rearranged order suggested by the proposed method and the default order. We assume the goal for testing is to collect FOBJ failing patterns. At first, the COT is tested until F collect failing patterns are collected. For chip I, define NI reorder and NI default to be the number of patterns applied until FOBJ failing patterns are observed. We assume test terminates when FOBJ failing patterns are collected in total. Test cost reduction is calculated using the 3 measures: represent, reduction count, and reduction percent. The figures show the test cost reduction of different FOBJ and F collect values of a high volume manufactured chip in 90 nanometer technology. When FOBJ is larger than 25, the probability that the reordered pattern wins exceeds 90%. The level of pattern reduction count is also significant. The greatest reduction count is over 500,000 patterns. Finally, the third measure, reduction percent, is as high as 35% compared to the default order.
In the second project, we combined several individual ML models to a comprehensive previewer, which works like this. First, from a set of diagnosed fail logs, we extract some features as well as the corresponding diagnosis outcome to train several predictors. They work independently to predict different aspects of diagnosis outcome. Once the prediction models are trained, they can be applied to undiagnosed fail logs so that each fail log can have a profile indicating the predicted diagnosis outcomes. Then practitioners can select and sort the fail logs according to their needs so that the most promising diagnosis can be executed first to best utilize limited resources. Here is an experimental example to verify the performance of the previewer. Say the goal is to execute n good runs of diagnosis which successfully report a single defect with resolution smaller and equal than 3. We compare the total number of diagnosis runs when the goal is achieved with and without the diagnosis previewer. In the case of n equals 40, 263 diagnosis runs are needed without the help of the previewer, which add up to a total time of 17 hours. In contrast, with the previewer, only 76 diagnosis runs and 1.35 hours are needed. When varying the value of n, we also see significant speedups brought by the previewer. For example, up to 9 times reduction in overall diagnosis runtime. The third subject is also associated with the diagnosis previewer, but here we focus on knowledge transferring when training data is limited, and the performance of the models degrades significantly with very little training data. For example, for a 28 nanometer test chip, 2,000 training samples are crucial to guaranteeing a 8% recall for diagnosis success prediction. The value drops to around 68% with fewer than 500 samples. Collecting sufficient training data, unfortunately, can be time-consuming. For example, one training sample may require several hours of diagnosis. Also, limited data inherently occurs during ramp-up. Therefore, it is necessary and beneficial to explore new frameworks to improve prediction performance when the amount of data is limited. On the other hand, many datasets generated during testing and diagnosis processes are highly correlated. For example, diagnosis data of different partitions in the same design or from different rounds of tape-outs. The correlated datasets could provide some prior knowledge as a supplement to the small datasets being focused upon. Based on this observation, the key idea is to borrow some prior knowledge from correlated datasets to facilitate model building. We suppose the current data at hand is quite limited, but we have a bunch of prior data which is correlated to the current data. The prior data are supposed to be sufficient in amount for training a good prior model, which encodes the prior knowledge. Then the prior model is adapted to the current data for a transferred model. Because this transferred model combines both prior knowledge and the information from the current data, it is supposed to have a better performance than the model that is trained purely on the current limited data. 2 groups of designs are used for experiments. Designs 1 to 4 are test chips for characterizing the manufacturability of random logic. They implement similar logic functions but are different in logic gates and layouts, so they are supposed to be highly correlated. Design 5 is a 28 nanometer test chip and design 6 is a 90 nanometer high volume part, so they are relatively less correlated. When a highly correlated prior dataset is available to provide useful prior knowledge, we observe significant improvements in model performance. For example, when predicting defect count, the transfer model outperforms the original model with different sizes of training sets and achieves 6-to-1 training data reduction. When the prior dataset is not so correlated, the performance improvement varies cases by cases. But when the prior knowledge is not useful enough or even misleading, we also have a strategy to detect such cases. The final project, LiDAR, uses various ML techniques to enhance diagnosis results towards high accuracy and ideal resolution. Many machine learning-based methods aim to train a classifier to predict whether a candidate corresponds to the actual defect. Different from other methods that trains the classifier based on simulation data, PADRI, as one of our previous works, uses real diagnosis results for model training. However, PADRI's classification performance is compromised by the labeling error caused by its intrinsic labeling process and limited training data. On the other hand, we found that there are other potential information not being fully used, like the correlation between labeled and unlabeled data, as well as the defect level information. So in LiDAR, semi-supervised learning and defect level learning are developed. And in the corresponding ITC paper, we also explicitly discuss the trade-off between accuracy and resolution to provide practitioners with guidelines on how to tune the ML algorithm for a specific objective. The overall flow of LiDAR is divided into 4 stages. LiDAR first takes as input the original diagnosis result from a population of failing trips. Each sample in the input dataset contains the extracted features of a certain candidate, but also includes the corresponding defect information. At first, all the samples are unlabeled. In the initial labeling step, part of them are labeled by 2 rules. And then semi-supervised learning is adopted to use both the labeled and unlabeled data to train a classifier and predict for all the samples. Then the defect level learning process follows to make good use of the correlation between similar defects so that to identify some obviously bad candidates to further improve resolution. Finally, a calibration procedure is employed to ensure accuracy. For example, if all the candidates of a defect are labeled bad, then all of them will still be kept in the list to assure accuracy. The performance of LiDAR is validated by 2 data sets. A virtual data set with all the ground truths of the candidates show that the number of defects with perfect resolution increases by 6.4 times. And the number of defects with resolution equals 2 increased by 2.4 times. Also, LiDAR shows significant advantage over PADRI for the number of defects with resolution improvement that ranges from 1 to 9. In addition, note that the largest resolution improvement resulting from PADRI is 91, while the number for LiDAR is 207. We observe similar trends in resolution improvement with another silicon dataset, and the diagnosis accuracy is verified by 6 PF8 chips. 5 papers associated with the aforementioned sub-projects have been published in the following journals and conferences. Finally, we really appreciate the fellowship and the opportunities it brought to us to cooperate with experts from the industry. Specifically, we would like to thank our advisors, Quan and Martin from Qualcomm, for their valuable time meeting with us, and their insightful and helpful advice.